So welcome everybody. If you're joining us on YouTube, so it's April 15th, the tax day. It's not really tax day, they moved it to July, but this would normally be tax day when your taxes are due. But we're not doing taxes today, we're doing calculus. We've had a warm up, so the students that are here live with us, they've thought about this warm up, and then we're gonna get a chance to go through it. So on Monday, we started introducing this idea of optimization. The idea of how do I find the maximum or minimum values of something. So often in life, this is what we want to do. We want to optimize. And so calculus gives us some tools to do that. So what we're going to do is we're going to remind ourselves what these words mean. Okay, so critical numbers. So a critical number is any time that the derivative is 0 or does not exist. Right, so what we're going to do is we're going to look around for critical numbers, places where the derivative is 0 or does not exist, and those are going to be candidates for our extreme values. Right, so those are the values we're going to want to check to figure out, are they local maxes or mins. Now, this word local means that it's only bigger or smaller than things that are close to it, but there could be a larger value somewhere else in the graph, right, somewhere in the domain. And so if we wanted the absolute biggest value, we would use that word absolute or global. So let's go ahead and see if we can find our critical numbers. So step one in this process is, let's go ahead and take our derivative, right? So we're going to get f prime of x here, which is 6x squared minus 6x minus 36. And I want to know, when is this function undefined, 1, and 2, where does it equal 0? Okay, so this is a polynomial, which means it's always defined. It has domain all real numbers. And so I'm only interested now in when it's equal to 0. And it seems like there's a lot of 6's and 36's in this, so I'm going to factor it first. Right, so I can factor out a 6, which will give me this, and it looks like I could quickly factor this other piece here into x minus 3, x plus 2. Right, and so when I look at this, this is my derivative, and it's always defined, and it has 2 zeros. So my critical numbers are going to be x equals 3 and x equals negative 2. Okay. All right, so critical numbers. Now what I want to do is look at my graph and try to identify, hey, where do I have a local max or a local min? Right, so these are my candidates. So as we saw on Monday, we're going to set up a sign chart. Right, so we're going to look at we call a first derivative sign chart. And I want to know, where does the derivative go from positive to negative or negative to positive? And so if we go back a few slides, on Monday we talked about this idea of the first derivative test, where if your derivative goes from positive to negative, meaning you're going increasing to decreasing in your graph, that's going to be a local max. And then correspondingly, if you go from decreasing to increasing, we are going to have a local min, right? So we're looking for these values where the derivative goes from positive to negative or from negative to positive. Okay, so I'm going to make a similar sign chart over here, and I'm going to put my values on it, right? So I'm going to have a negative 2 and a 3. Okay, so what we've done is we've broken up you can think about this as the real number line if you want, and I've broken it up into 3 intervals. Okay, so numbers that are smaller than negative 2, between negative 2 and 3, and then bigger than 3. So in these intervals, what I want to do is go through and test, is my derivative positive or is my derivative negative? Okay, so what we do is you just go ahead and pick a value that's over here, right? So you think about a number, say negative 3, and what I'm going to do is I'm going to plug it in, right? So I'm going to ask my question here, f prime of -3, is it positive or is it negative? Okay, so I could go ahead and compute this value and do all the multiplications, but I don't have to do that. Okay, so I can do a little bit less work because really I know it's the product of these three terms. So when I plug in -3, I'm just going to ask myself, do I get a positive number or do I get a negative number? Right, so over here, what I'm going to get is I'm going to get 6 times, well, if I plug in -3 minus 3, that's a negative number. And then -3 plus 2, that's also a negative number, right? So I'm going to get 6 times a negative number times another negative number, which means that this is a positive number. And I don't actually care about what the number is. I just care about, is it positive or is it negative, okay? And so we can go through and we can pick another number in this interval. And so 0 is a nice one. Anytime I can pick 0, I do that. And so if we go through, we're going to get 6 times a negative number times a positive number, which means, hey, this thing is negative. And then if I plug in, say, a number over here, something that's bigger than 3, I'll pick 4. Right, when I plug that in, I'll get 6 times a positive number times a positive number. So if everything is positive, then I get a positive number over here. All right, so the graph of my function, it goes something like this, right? So it's increasing to some point, and then it's decreasing to another point, and then it's increasing to a point, right? So if you think about this, right, so in this area right here, you can see that we're going up to a point, and then we're coming back down. So this value right here, what I should find is that this is a local max. And then as we keep going, right, this is decreasing into increasing. And so this value over here, this is going to be a local min. Okay. So we have it all on the screen here, right? So we do these sign charts to try to identify where our functions are positive, negative, which corresponds to increasing and decreasing. And that helps us find our local maxes and mins. All right, so I want to pause here, kick it over to you all, and see if there's any questions about this stuff. So far, so good? You remember this from pre-calc, yeah. So you might have done some of this stuff where you look at sign charts in pre-calc, yeah. You find maxes and mins. Probably in pre-calc, though, you didn't take derivatives, so you probably weren't using these ideas here where you take derivatives. Good? All right, so what I'm gonna do, I'm gonna flip over to our book again. All right, so normally what we would do is print these out, but our new remote learning format. So let's see if we can think through this activity 3.1.2. Okay, so we're given the function, and one thing that I want to point out here is what we're given is the derivative. Okay, so in this activity, the author of this book is giving us not the original function, but they're giving us the derivative, right? So we don't have to take the derivative, we are being given the derivative of the function, and then we want to go through this thought process and see if we can figure out what the maxes and mins are of these functions and where they might occur. Okay, so we'll think through this one. We'll give it a minute or two, and then I'll see what you all think.
So you're just trying to find when the numerator is 0?
That would be part of it, yep. So one of the things you're going to do is look for where the numerator is 0, but there's a little bit more to it than that in this particular case. So any ideas? What do you think? What are our critical numbers?
-4, 1, and 2.
-4, 1, and 2. All right, so I agree. Those are our critical numbers. So Caleb, if you just looked at the numerator, you would get -4 and 1. So where did that 2 come from? All right, so the numerator is going to be 0 at -4 and 1. And why do we have a 2 in there?
Because it's undefined at 2.
Yeah, right. So, yeah, right, exactly. It's going to be a vertical asymptote there. And so what we're going to think about is, we have the points where it's 0 or undefined, right? So you're not only looking for zeros, you're also looking for where it's undefined. Okay, so what we're going to do, let's go to part B, right? So I have a sign chart up here on the blackboard. And so what we're going to do is we're going to look at G prime, and we said we had these values, -4, at 1, and at 2. Okay, so when we set up our sign chart, we're going to ask ourselves, hey, is this function increasing or decreasing in each of these intervals? And we're going to figure that out by plugging numbers into the derivative, right? So we have these 4 intervals here, and we're going to have to determine, hey, is our function positive or negative at these different points? Okay, so again, if you wanted to compute the exact values of these things, you could go and plug them into Desmos or something, plug in different values. It would give you the right. So it would give you the exact numbers. We don't actually need them in here, so I'm not going to jump over to Desmos. We'll just kind of think, hey, are these things positive or negative? So one key here that I always pick out is, hey, x minus 1 squared, right? No matter what I plug in here to this thing, this is always going to be a positive number, right? So when we're going through thinking about, hey, which of these values are going to give us positive or negative numbers, this one always gives us a positive number, right? So these two could potentially change from positive to negative, and so we'll keep that in mind. Okay. So to start, what we could do is we could go ahead and, let's say, pick a value, right? So I'm going to think about -5. You don't have to think about a value. You could think about a range, but it's often helpful to think about a value here. So if I plug in -5, this gives me a negative number. This is always positive. Okay, so I have some structure that looks like the following. I have a negative number times a positive number, and all of that's going to be divided by a negative number. Okay, so in my numerator, I get a negative number, and I'm divided by a negative number. So the result of that is positive. Okay, so again, I don't need to know about the actual numbers. I just care about the sign. Is it positive or negative? Okay. So if we keep going, right? So if I pick a value over here, right? So 0 is in this interval, so I often like to think about 0 if I can. So I will get the form, right? I'll get a positive number times a positive number, all divided by a negative number. Right, so if you want to think about it this way. So that result is negative. All right, so if we keep going here, right, I can pick a value 1.5. And so the structure that I'm going to get is a positive number divided by 1.5 minus 2 is still a negative number, right? So this is going to be negative. And then if I go over to 2, I can pick, say, the value 3. And going through, I think they're all going to be positive at this point. So we get a positive value, and then a positive value. And so this is going to be positive. Okay, so going through, what we see is, right, so I have, we're increasing, we're decreasing, we are decreasing, and then we are increasing. Okay, so this would be our first derivative sign chart. And it looks like we could maybe pick out some values. So do you see any local maxes or mins that are happening here?
Max at -4 and min at 2.
Min at 2. So are we sure that there's a local min at 2? Right, so we have to be careful about what we know. So if we look in the chat, right, so Luke reminded us that 2 is a vertical asymptote, right? So this is really a vertical asymptote for our function. Right, so this is a vertical asymptote. So our function's not actually defined at 2, so it will decrease, right? So it's decreasing to this vertical asymptote and increasing out of it, but there's no actual value there, right? So this 2, it's giving us this idea that this is a vertical asymptote, so it is not defined there. Okay, so this was part B, right? We decided local max, local min, or neither, right? So this is a vertical asymptote, and then this is neither, right? So it's not a local max or min. It's just decreasing. The derivative becomes 0, and then it decreases after that. Right? So just from looking at the derivative, I'm actually getting a lot of information about my function here. So give ourselves some more space. So part C of this function asks this question, hey, is there a global max? So what do you all think? Any ideas from this? So would the global max be -4, 2? Okay, so what we know is that if I look over here, right, so values that are a little bit less than -4, they're going to be smaller than this local max, or anything close to here is smaller than this local max. And if I look to the left, from -infinity until -4, it was increasing, right? So the graph increases. It increases all the way through here till it gets to this point, whatever it is. Then we're decreasing, and then we're decreasing, right? So it looks, if I'm looking over here, it looks like, yeah, this could be potentially the biggest point. But then we get over here, and then now our function's increasing, right? So from +2 out to infinity, this is just increasing. So is it possible that this somewhere over here, it takes over, it gets higher than this local max? Yeah, so somewhere over here, right? So if we just go off to infinity, right? So as our inputs get bigger and bigger, our function just keeps going up, 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 right? So this is increasing, right? It might be increasing very slowly, but if we keep going out forever, right? So if we continue off in this positive direction forever, I would expect that this goes off to infinity, right? So if a function just keeps increasing, 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 then it's not going to ever level off, right? It's never going to stop getting bigger. So at some point, if you go out far enough, it will eclipse this value. Okay, so correct. So in this particular case, we don't know. So I would expect that, like, there's this over here is telling me this function just keeps going off to infinity. And then if we look over here, right, if I'm sort of going backwards, right, the function's increasing up to this point. So the more I go left, the more negative my inputs are. We're going to keep going down, 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 down in our outputs, right? So these sort of behaviors right here tell me, hey, there's not going to be any global min, right? Because these will keep going down forever, and there's not going to be any global max because this will go up forever. The one consideration is if you capped these, right? So if you looked at this on a particular interval, right? So if you looked at it on a closed interval, if I said, hey, I'm only going to consider this up to 100, and I'm going to stop, then you would have a max somewhere. And similarly, if you capped it on the other side and said, I'm only going to look between negative 100 and 100, then you could identify maxes and mins because then you'd have these endpoints that you could consider. But the way the problem is stated, we're considering these values to go off to infinity, so there would be no max there. Okay, so answer to that one is no. And then, so we kind of talked about part D of this. It asks, what happens as our inputs go off to infinity to the derivative, right? It keeps increasing, so we'd have no max. And then part E is let's sketch a graph. So with this information here, can we sketch a graph of this function? So let's try this out. So you all have the annotate tool. So here's all our information. We've got 5 people here. So can we sketch some graphs? So if you use the annotate tool, we have all our information here, right? Can we maybe sketch some graphs down here at the bottom? Yeah, right. So we'll see sort of what comes in. Right. So as you're playing along at home, let's see if we can sketch some graphs, and we'll talk about them. I see somebody drew some axes in, and then somebody drew a graph. So the orange graph on the left here, whoever drew that, I would think about some things, right? So one thing in particular that you're missing is it's pretty cool. They're all drawing graphs. So.
No.
we're close. We're close here. So see if I use my pointer. So keep going, right? So this graph over here, whoever's drawing this one, this green one, keep going, and the pink one, keep going. So orange graph over here. I don't know who's drawing this, but so vertical asymptote. Remember what happens at this. So the graph is going to should get close to this vertical asymptote. So whoever's drawing this one, I would encourage you to rethink what's happening around 1. Oh, I don't know who's doing green over here, but you were doing great. You were doing great. Let's get some ideas here. This is working out well. I like this. We're all drawing on the screen. Feels like we're actually in the classroom. Yeah, we're close here. So as we are observing, right? So we can all see other people's work. So we have a bunch of different graphs here, and honestly, I have no idea who drew which one. So I don't know that I have any way to tell. You don't have to label them, yeah, if you don't want to. So if you don't want to put your names on it, you don't have to. Right? We don't need to know who did what. But so yeah, we've got a couple different graphs up here, and so a few things that are going on. So the orange graph over here, as I commented on. So what we should be seeing, right? If this is a vertical asymptote, yeah. If this is a vertical asymptote, if this is a vertical asymptote right here, we should be seeing, right? So the graph sort of gets close to it as we see in the other ones, right? So what we see over here, so I can't actually go over to some of these. Can you all see this mouse cursor? Can you see this?
Yeah.
Okay, excellent. So these vertical asymptotes right here, right, this is what they should look like. So as I'm going on this graph, I'm just sort of picking off these pieces of information. Are we increasing? Is there a local max? Are we decreasing? Is it neither, right? Do we go decreasing into a 0 derivative into decreasing at 1? That's sort of a tricky one. And then do we have a vertical asymptote? And are we increasing after that, right? So there's all these things, you can just sort of check them off, right? So if we just go left to right, it's increasing to a local max, which is great. It's decreasing. I'm not so sure over here, right? There should be a neither, right? So you should see like the derivative is 0 right around here somewhere, and it goes decreasing again. So I'm not sure that the derivative is 0 at that point or anywhere in here. And then we should have a vertical asymptote. For this one, right, so for this purple graph, again, we're increasing to a local max. We're decreasing. Do we have a point in here where the derivative is 0? Again, on this one, I'm not so sure that we do. So we should see something sort of flatten out. Again, increasing to local max. Maybe this is a point right here. Maybe we have a 0 derivative, right? So if we're trying to go here, if that's what this is, you could maybe imagine that this was flattening out here around 1. So the pink, yes, and then the orange in the middle here are similar. Again, this is the one that's missing, but I would say the most accurate graph is probably this green one where we're increasing to local max, decreasing. We flatten out right here, right? So you get this, it's really flat. So you'd have a 0 derivative, it's decreasing down to our vertical asymptote, and then we're increasing out of it. yeah, so this is basically from this information, we only have the derivative, but we got a lot of good stuff happening, right? So we can pretty much understand what's going to go on. Now, what we don't know is how high up is this, right? So what is the output here? That's one thing we don't know. So if we really were interested in what that maximum output is, this isn't the information that we're going to use to get that, right? So we can't actually tell how big that local max is, but we know that that's where it's going to occur. Okay, so this is going to continue this theme of, hey, if we know how fast something is changing, right? If we can measure precisely how fast something is changing, then that tells us a lot about what's actually happening. So to bring it back into sort of our current pandemic context, right? What we can measure about the pandemic right now is, hey, how fast are things changing, right? How many new cases are there each day? How many new tests are given each day, right? These are derivative numbers. How fast are these quantities changing over time? And if we can do that, if we can measure how fast they're changing, then we can make predictions about what's actually going on with the number of cases, with the testing, and all sorts of things, right? So a lot of math modeling going on right now, looking at rates of change and then trying to bring it back to, making predictions about what's actually happening, right? Where are we going to see peaks? Where are we going to see valleys? And so forth. Okay, so questions about this so far? Did this feel pretty good? I mean, you all drawing the graphs in here, I thought that was great. So it seemed to me like we felt pretty good about that. Okay, so what I want to do now is jump back to our picture here, but the first derivative test. So I'm going to go ahead and get rid of our graphs, but we have them on the video. Okay. So we're going to get rid of our graphs, and we're going to look at this first derivative test again. And one of the things that came up with the first derivative test was this ability to identify local maxes and mins. But what we're going to do now is we are going to, I don't want to cross out the first derivative test, but in red, we're gonna call this also the second derivative test. Okay. So I'm going to use the same pictures. And do we remember what kind of information we get from the second derivative? So first derivative told us when functions are increasing and decreasing. What did second derivative tell us?
Concave up and concave down.
Yeah, concave up and down. So if I just look at these pictures and I start thinking about the second derivative, if we're going to have a local max, and I wanted to use the second derivative to tell me about a local max, what should I see, right? So in this particular case right here, how would you describe the second derivative? Right, so this graph is concave down, so the second derivative is
Negative.
That's right, yeah, so our second derivative is negative. And then correspondingly, right, concave up, our second derivative would be positive. Okay, so just in the same picture, right, so if we have information about the first derivative, we can identify sort of how fast our quantities are changing. Then we can identify these local maxes and mins with the sign charts. But at times, those sign charts get a little bit much to keep, plugging in all these values. So if you do have access to the second derivative, right, so if you're able to compute the second derivative, what we can do is, instead of looking at a sign chart, right, so instead of looking at like all the values to the left, values to the right, all we need to know is, hey, at this particular point, if we're concave down, then that's a local max, and if we're concave up, then that's a local min, right? So the second derivative gives us some additional power here to tell if we have local maxes and mins. Okay, so let's jump back over to the book and see the formal statement. Okay, so the second derivative test tells us this. You have a critical number, and right, your first derivative is 0, and then your second derivative is not 0, then you have a maximum if and only if you are concave, right? So this is telling you you're concave down, right? And has a relative minimum if and only if you're concave up, right? So there's lots of information. There's some caveats in this statement. So we need to have the case where our first derivative is 0, right? So the cases where our first derivative is not defined, if our first derivative is not defined at a particular point, it is a critical value, but we're not going to be able to use the second derivative test because we're not going to be able to find the second derivative at that point, right? So first caveat, the first derivative has to exist. This test only works when you have critical values where you get a 0. But it's useful at times, right? So at times it gives us this one numerical condition that we have to check rather than checking over particular intervals, okay? And so one of the things that comes out of this that we haven't really talked about a whole lot so far is this idea of an inflection point, right? Where does our graph change concavity? Okay, so if I want to go back and look at a particular function and say, hey, where does it go from concave up to concave down? We're going to give that point a name, and then we're going to call it an inflection point. Okay, so two ideas that are coming out of this next section right here. The second derivative test, we can test for local maxes and mins, provided that we look at the second derivative and match it up with concave up, concave down. And those points where we change concavity, we're going to call inflection points. All right. So with these two ideas in mind, let's go back and revisit our warm-up from the beginning of class today. Okay, so here's our test. And so here was our warm-up at the beginning of the day, right? So we did this about 40 minutes ago. Right, so I'm gonna downsize this. I'm gonna put it over to the side. This is all our work from earlier. Okay. Is that too small? Can you all still read that or sort of see that work over there on the side? Yeah, still good? Okay. So it'll give me some space to write. And then we've seen that, right? We've seen this earlier. All right, so what if we did the second derivative, right? So it took us a while to do this whole sign chart right here that we saw earlier. But what I can do now that we've sort of thought through the second derivative is I can go ahead and take the second derivative of my function. All right, so my first derivative is over here. I'm actually going to use this piece, right? So I'm going to use the expanded out piece to take the derivative. And so what we'll get here is, all right, we get 12x minus 6, right? So our second derivative in this case is actually particularly nice, right? And so our critical numbers were -2 and 3. Okay, so what we're going to do is I'm going to test, right? So I'm going to test f double prime of -2, right? So that is a negative number, right? So it's a -30. Right? We don't actually need to know the number. We just need to know that it's negative, right? So f double prime of -2 is -30. So our graph here is concave down, which implies that we have a local max, right? So with one numerical check, instead of sort of plugging in two different values, we're able to come to the same conclusion that we do have a local max at this point at -2. And then if I also look at f double prime of 3, if I had to plug this in, I get +30, which means it's concave up, which tells me that we have a local min, right, by the second derivative test. Okay, and so that matches up with what we saw before. Okay, local min right here. Okay, so what about inflection points? Right. So one thing that I'm going to be interested in soon is inflection points, which is where does the graph change from sort of the derivative is sort of the graph's getting more steep to where it starts to slow down, right? So where is our concavity change, or where does our derivative sort of start to slow down? Where does our rate start to slow down? And so that's going to be where this is equal to 0. So when we look at this graph, we should see a change in concavity when f double prime is equal to 0, or where we have 12x minus 6 equal to 0. And so very quickly here we get x is 1/2. Right, so this should be our inflection point. Right. All right, so let's go back over to Desmos in our last minute here. And let's take a look at our graph, right? So here's the graph of our function. And if we put all this together, we should be seeing that we have a maximum, a local max at -2, right? So we do in fact have that. We have a local min at 3. And then our inflection point, what we should find is that the graph changes concavity at 1/2. Now, on this scale, it kind of looks like it's somewhere in this range, but when we zoom in, right, so this is going to be the exact point where we change from concave down to concave up, right? So the graph's kind of like this over on the left, and then it becomes like this over on the right, precisely at this point right here. Okay. Now, to highlight what we're going to be doing later, right? So what I have here is some data from the pandemic. So this is data from the COVID-19 cases in the U.S. So data is from this website, which is from Oxford, and so what I've been tracking for the last 36 days is the number of cases in the U.S. And so we have, as of yesterday, it was at 609,000. But if we look at the shape of this graph, we can see that, hey, we're actually looking, we can actually tell concavity here. So one of the functions that we're going to explore in section 3.2 is called a logistic function, which models pandemics, disease spread, population growth. And so we can see here what we're particularly interested in is the inflection point of this graph, right? We want to know, hey, things are getting, when do things start to get better, right? When is that rate starting to slow? When are we starting to see, when the people say flatten the curve, right? We're particularly interested in finding the inflection point of this graph. So over here, things are growing faster. And then once we get to the inflection point, which is down here somewhere, it looks like, then things are going to start to slow down, right? And so that's a good sign for us in society. We're particularly interested in the inflection point of this current wave of the pandemic. So if you're modeling it, and you think about this logistic function, that's what we're interested in, right? That inflection point. When do things start to slow down, right? When does the derivative start to level off here, right? When does it start to, doesn't decrease, but it slows down, right? So it starts to slow down. The derivative is no longer increasing anymore, right? So I've been collecting this data, and so what we'll do is we'll see in section 3.2, we'll go through sort of this definition of a logistic function, and we'll learn all the different parameters behind it. Maybe we'll come back and revisit my model that I'm building here, so we can see sort of from a calculus sense, all this modeling that's happening, all this data that you're getting from the news, we're going to try to make some sense out of it on our own and see if we can use some of our own math knowledge to make. I don't know that we're going to make our own predictions, but maybe we'll just be able to get a better sense of control over our own understanding around what's happening. So something to keep in mind for the next week. So on Friday, what we'll do is we will finish up this section 3.1. We're basically done. We've seen all the things, but we'll look at a couple more examples of finding inflection points or something. Maybe we'll do this problem 1, and then we're going to move into section 3.2 where we start to introduce parameters. So we're going to look at what we call families of functions, and lots of cool interactives there. So for those biologists out there, we're going to look at a model where we look at where we take medication and sort of how our body processes it. And so it's called a surge function. So that'll be a cool one. It's usually a pretty cool one. So, all right, I'm going to call it here. We're a few minutes over. But any last questions before we go? All right. I'll see you all on Friday. Stay safe. Thanks.